then this sequence or this part is already satisfied. This condition is already satisfied. Let's check the second condition. That is that the sequence is decreasing. In other words, is 1 over 2 to the n plus 1 less than or equal 1 over 2 to the n? Well, in this case, check the denominator on the left hand side. That the denominator has a power n plus 1 versus the right side of the inequality is just an n. So that larger power is going to make the denominator bigger, and the overall result will be a smaller number than on the right hand side. So the two conditions are satisfied over here. All right. So let's see. So now we can proceed to check for absolute convergence. That is sigma n equals 1 to infinity of the absolute value of -1 to the n plus 1 over 2 to the n. Well, again, when we have the absolute value here, that absolute value cancels out every alternating factor, because with alternating factors like this, what they do is make, or rather output values between -1 and 1, and well, since we have absolute value bars, those negatives become positive, so really those alternating factors just vanish, just go away. Alright, so that's going to leave us with the following series: n equals 1 to infinity, 1 over 2 to the n. And well, can we rewrite this function, or rather this series, in a different way? In a way that we can recognize maybe a special form? And if so, how can we rewrite this one? Any ideas? 1/2 to the n? And well, what about this series? What do we know about it? It's a convergent geometric series, right? Well, in this case, this is a very simple series. We don't have to do any comparison test. We don't have to do anything weird. So we're essentially done. Because the new series converges, the original alternating series will converge absolutely in this case, right? So sigma n equals 1 to infinity, -1 to the n plus 1 over 2 to the n converges absolutely. So notice in the previous exercises we had to use a comparison test, you know, on both of them. In this case, well, we just got a direct geometric series, you know, and it happened to converge. So the original alternating series will converge absolutely. All right. Let's look at the last example for this section. Sigma k equals 1 to infinity sine k over k cubed. All right. Well, even though this doesn't look like an alternating series, because it doesn't have a -1 to the k or a -1 to the k plus 1 or minus 1, well, the factor in the numerator, sine k, that bounces between -1s and 1s, so that's what makes it an alternating series. So let's note that. Note that sine k is varies between -1 and 1, which is what makes it an alternating series. So in this case, well, we can check the two conditions for convergence. That is, limit sine k over k cubed as k approaches infinity. All right, what is this limit equal to? And I know what you might be thinking about this one. You might be thinking of doing the L'Hopital's rule maybe 3 times. But the problem with doing the L'Hopital's rule is that in the end, you will be left with only a trigonometric function, sine or cosine. I'm not sure which one is it going to be. I haven't done it, but just by looking, that's what I'm thinking it's going to happen. And well, you're left with just a trigonometric function evaluated at infinity. Well, a trigonometric function at infinity is just bouncing back and forth between -1 and 1, which makes it a DNE. All right, it's a DNE, and it's not a limit, and it's not a zero limit, which is the requisite. However, in this case, we're going to look at the rate of growth of the functions. Well, sine of k only bounces between -1 and 1. That is, its minimum value is -1 and its maximum value is +1. So regardless of the case, -1, for example, in the lowest value, -1 divided by k cubed, which is infinity cubed. What's -1 divided by infinity cubed? And what about the highest value, which is 1? Still the same, or any value in between, 0.93, 0.5 divided by a big number cubed. Regardless of the value, this is going to be 0. So the first condition is satisfied. All right. So number 2, the second condition is that sine of k plus 1 over k plus 1 cubed. Is this decreasing? Well, whoops. Well, I mean, even so, let's check the values of k. We have a k plus 1 and a k, but we have the opposite sign. We would have thought of the inequality sign the other way around in order for this to be true. However, it is the denominator, which is a quantity cube, what grows a lot faster. And well, k plus 1 cubed versus just k cubed, for sure this is going to be a larger number in the denominator, making an overall quantity a smaller number, and that meets the inequality condition here. So we can go ahead and proceed to find absolute convergence. Recall again, just to check with our diagram, let me go back a couple of pages, or 1 page actually. So the first 2 conditions have to be satisfied in order to go this route, the convergence route, so we can check whether the convergence is absolute or conditional. However, if at least one of these 2 conditions is failed to be satisfied, well, diverges and you're done. You don't have to check anything else, all right? Well, for these situations, I set up these exercises so we practice on finding the absolute value of the series, create new series, use all the techniques that we know so far. All right. So sigma n equal, or k rather, k equals 0 to infinity of the absolute value of sine of k over k cubed. All right. Well, so the way we are going to, express this, well, let's leave the absolute value of sine. Let's leave it as an absolute value of sine, because it depends on the different values, whether it's going to be positive or negative. And k cubed, well, for values from 0 to infinity, k cubed is always positive, so that's why we don't need absolute value bars. But for the trigonometric function, we will, because from between 0 and infinity, sine bounces between -1 and 1, so we need to specify these absolute value bars. This one? Yeah. Yeah. Wait a minute. No, it's supposed to be 1. Otherwise, we're in trouble, right? Yep. Thank you. Yeah, the denominator would be 0. Yes, we're in trouble there. All right. Well, in this case, this is not a direct series like the previous one. So we need to use the comparison test. All right. Well, can we compare with something simpler? Again, when it comes to comparison of series, try to come up with something as simple as, number 1, a geometric or or a p-series? That's mainly what we try to get here. So which one would be a good idea? 1 over k cubed, which is a p-series. So compare with sigma 1 over k cubed, k equals 1 to infinity, and well, in this case we know that this is convergent p-series. Alright, so that's a convergent p-series. That is, when we use the direct comparison test, we need to show that tiny is less than or equal to small. Alright, so that is, the problem A7 has to be less than or equal B7, and in this case, well, is absolute value of sine of k. Well, yeah, even the absolute value is fine. All right, but I'm gonna take just sine k without the absolute value bars anyway. So is this inequality true? No, some of you say no, some of you say yes. Well, let's think about this one. Okay, the denominator k cubed, oh, less than or equal. So k cubed, yes, less than or equal. K cubed can be less than, well, in this case can be equal to k cubed. So no problem here. But what about sine k? Well, what's the maximum value attained by sine? So in this case, I think that could be either less than 1 or also smaller than 1, right? Or equal to 1, right? When it attains its maximum. So this is true. This inequality is true. So that means, well, this series right here converges. Well, because we got convergence, so sigma k equals 1 to infinity of sine k over k cubed converges absolutely. Alright, I would like to take a slight detour here. Alright, so how can this fail? So sometimes we feel more comfortable with the limit comparison test because taking a limit is potentially easier than comparing quantities sometimes, especially when it comes to show that something is tinier than small, that something tiny is less than or equal to small, or something huge is greater than big. Well, what if instead you use the limit comparison test? Well, limit, the original, which is sine of sine k over k cubed divided by 1 over k cubed as k approaches infinity. So that would have been limit sine k over k cubed, and well, times the reciprocal of 1 over k cubed, which is k cubed over 1, which actually cancels. Alright, well, actually, oh no, that it's not, there's nothing wrong with this. Actually, I'm going to keep the absolute value bars. Alright, and so that's going to leave us with limit, with the limit between, limit of sine k as k approaches infinity. Alright, but what's going to happen with this limit? What is that limit of sine at infinity equal to? Well, just sine with, let's ignore the absolute value bars for now. It bounces between -1 and 1, right? So we would potentially, well, how about I write absolute value of limit sine k. So we can interchange the limit symbol with the outermost function. Well, sine of k, well, that essentially bounces between -1 and 1, or rather to the k, all right? But I mean, what's the absolute value of this? It's just 1. Is this positive? Finite? However, computing the limit, it's a little weird, isn't it? Because if we forget about the absolute value bars, because if we do anything weird, could be confusing. So I mean, I'm showing you both ways to test this function. You get to choose whatever you feel more comfortable with, all right? So, well, so this is the end of this section. Let's get to the next one, the next section, which is going to teach you the last two techniques to check for convergence and divergence. All right, that's the ratio test and the root test. All right, the ratio test, it's primarily used when we have all right, commonly used, or rather, the best technique for series involving factorials. You might remember how we worked with factorials at the beginning of the chapter when we looked at infinite sequences. How did we simplify those factorials to divide out some of the factors, to write expressions without involving those factorial symbols? Well, that's going to come back. And notice we haven't worked with any series at all involving factorials, so this is the time. So this is what we're going to do. So we are going to write a sub n plus 1, and we're going to divide it by the original a sub n, take the absolute value, then the limit at infinity, and three possible case scenarios. Number 1, the limit is less than 1, the series is convergent, and it's actually absolutely convergent. Why is that? Because, well, we're taking the absolute value of the series. So we're taking the absolute value, it converges from something that is an absolute value. Well, it converges absolutely. What else? So if limit is greater than 1 or infinity or dne, the series is divergent. However, in the third case scenario, if the limit is exactly equal to 1, the ratio test is inconclusive, and then we will have to go about a different test. All right? So let's look at some example. Also, this is I don't have enough space. Well, this is an alternative for alternating series. Alright, this is something we can do because actually our first example will be an alternating series, as you will see. Alright? So, let's look at one example. Number 1, sigma n equals 1 to infinity of -1 to the n of n squared over 3 to the n. So, number 1, we need to set up a limit. What limit? Well, limit of absolute value a sub n plus 1 over a sub n as n approaches infinity. Well, limit that a sub n plus 1, that actually implies or it's indicating that we should change every instance of n in our general rule with an n plus 1. In other words, and it's going to look big, so -1 to the n plus 1, n plus 1 squared divided by 3 to the n plus 1. And then we're going to divide by a sub n, where a sub n is simply the original series. Negative 1 to the n squared over 3 to the n, as n approaches infinity. All right. Well, don't feel overwhelmed about this huge quantity. There's a lot of things that are going to simplify pretty nicely. Number one, so these alternating factors, we can just cross them out, because what do we have? Isn't it an absolute value outside of the expression? That absolute value gets rid of those alternating factors. Whatever negatives come out of them, they become positive, so no need to keep writing anymore. So what we can do about this big expression is, number one, well, what do we have? A fraction being divided by another fraction. When we divide a fraction by another fraction, we multiply the fraction in the numerator by the reciprocal of the fraction in the denominator. In other words, this is limit n approaches infinity, n plus 1 squared 3 to the n plus 1 times 3 to the n over n squared. So let's do some algebra on this limit and simplify as much as we can, and then compute the value of the limit. So number one, what do we have? So a few things that we're going to do here is cancel this 3 to the n with a 3 to the n that comes up from rewriting the 3 to the n plus 1 using laws of exponents. And I'm going to expand this binomial n plus 1 squared, limit n approaches infinity. So that's going to be n squared plus 2n plus 1 divided by 3 to the n times 3 to the first powered by laws of exponents. Again, what law of exponents is involved? It's a to the, or rather, yes, a to the m plus n, a to the m times a to the n. Alright, that's what's going on over here. Alright, so that times simply 3 to the n over 3. Oh, not 3, actually, n squared. So, a couple things we can already do. Cancel out the 3 to the n. And, well, that's going to leave us with a 3 in the denominator, or rather 3n squared. So this will be limit as n approaches infinity. That's n squared plus 2n plus 1 divided by 3 times 1, 3 to the first power, which is 3 times n squared. Alright? And I think from here we can take the limit. That's because, well, what do we have? Polynomial over polynomial. Yes, that's only one term, but it's technically a polynomial. It's a second degree polynomial. Both of them are second degree polynomials. So we can just go with the ratio of the leading coefficients in this case. The limit is 1/3. But in this case, now we need to check with the conditions for the criteria for the ratio test. So either we check for less than 1, greater than 1, or equal to 1. In this case, 1/3 is less than 1. That means converges. Converges by ratio test. Converges by ratio test. Alright. Let's look at another example. Letter B. Sigma n equals 1 to infinity, n factorial over 5 to the n. Well, here is where we're going to work with the factorials finally. So number one, this is limit. Let's do the whole setup. Limit a sub n plus 1 over a sub n as n approaches infinity. That's limit of n plus 1 factorial over 5 to the n plus 1 over the quantity n factorial over 5 to the n. That is the original series. Yes, the setup usually looks this nasty. However, we'll divide that simplify that complex fraction by multiplying by the reciprocal of the denominator. Alright? So this is limit n approaches infinity. That's n plus 1 factorial over 5 to the n plus 1 times 5 to the n over n factorial, which is the reciprocal of the fraction we have in the denominator in the previous step. Alright, so let's do the algebra here. So number one, again, we're going to use laws of exponents to rewrite 5 to the n plus 1 as 5 to the n times 5 to the first. And, well, what about the numerator? So that's 5 to the n times 5 to the first. So we have to simplify factorial. So you might recall from the beginning of the chapter that we expand the factorial that gives us the largest value. In this case, the largest of the factorials is the n plus 1. So we can expand that n plus 1 factorial. So there's multiple ways to expand this factorial. That is n plus 1, 1 less, that's n minus 1, n minus 2, you know, depending on our needs. However, I don't think we need to expand too many factors because we're going to expand it until we match with the one in the denominator, which is in this case only one expansion. That is n plus 1 times n. Well, that matches with the n factorial here. So that's our n factorial here. We're going to stop there. All right. And that's 5 to the n in the numerator, so we can divide out 5 to the n, 5 to the n, n factorial, n factorial. So in this case, we're left with limit of n plus 1 over 5 as n approaches infinity. And well, this limit is, well, infinity plus 1, which is infinity. And even if you divide infinity by 5, it's still infinity. Well, because the limit is larger than 1 or infinity or DNE, the series in this case diverges. By ratio test. Alright. Well, in this case, you can sort of, you know, predict that this series will diverge, because if you analyze the quotient, what do we have in the numerator? We have a factorial. In the denominator, we have an exponential function. Both functions are powerful. I mean, grow really fast. However, it is the factorial the one that grows a lot faster than the exponential. And then we have a larger number in the numerator, so we would expect for this series to blow up to infinity, which is exactly what we have in this case. All right. So let's have a look at another example. Sigma n equals 0 to infinity, negative 1 to the n over n squared plus 1. Alright, so what about this one? Well, again, that's another alternating series. So let's set up the whole limit first and see what's going on and see what's going to happen about this one. So limit n approaches infinity, that's negative 1 to the n plus 1 over n plus 1 squared plus 1 divided by negative 1 to the n over n squared plus 1. So again, the numerator part is everything shifted by n plus 1. That's the a sub n plus 1. And the part in the denominator, it's the original series. All right? So, well, number one, again, these absolute value bars cancel out these alternating factors, again, because whatever negative outputs we get from those alternating factors, they're just going to go to positive. So we can just cross them out. Then we have the limit of, that's, well, number one, That's 1 over n plus 1 squared plus 1 times n squared plus 1 over 1. So that's because in this case, when canceling these alternating factors, we're left with invisible ones, if you will. So that's going to give us these couple of fractions there. And well, let's simplify this fraction, or rather write it in a nicer way and expand the denominator. The limit as n approaches infinity, that's n squared plus 1 over n plus 1 quantity squared. Let's expand the binomial there. That's n squared plus 2n plus 1 plus an additional 1. And simplifying all this, we should get n squared plus 1 over n squared plus 2n plus 2. Well, again, we have a polynomial over polynomial, so what's this limit equal to? 1. Well, what does the ratio test tell us when the limit is 1? Test inconclusive, right? So in this case, we would have to go about a whole different test. Maybe the alternating series test. I think we did this one in the alternating series, right? Let me check. No, I don't have those notes from here. I think we did this one. So test inconclusive. Yes, I think we did this one or something similar. So what's going to happen? So yes, this is decreasing, and also the limit of the sequence will be 0, all right? And when we take the absolute value of the series, that's going to become n equals 0 to infinity, 1 over n squared plus 1. And this one we compared with 1 over n squared, which is a convergent p-series. And in this case, yes, this one is tiny, this one small. So this new series converges, the original series converges absolutely. If we had to go through with an alternative series. So we need to go back to the alternating series in this case. Okay? All right, letter D. Letter D, it's a weird one because we have this weird looking product right here, which looks like a factorial. But it's not quite a factorial, so the factorial actually goes in reverse order, in descending order, like when we have a 5 factorial, what do we do? Well, multiply 5 times 4 times 3 times 2 times 1, so multiply all the numbers below n, but in this case, check the direction of the product. We start at 2, 4, 6, and it gets bigger every time. In an actual pattern, the pattern is 2n. That is, we're multiplying the first even numbers, right? And in the denominator, we have the sequence 2, 5, 8, which is given by 3n plus 1. So number 1, how about we have a look at how do we compute this sequence? For example, for n equals to 1, this is what we're going to do. We're going to multiply just 2 times 1 over 3 times 1 minus 1, which is n equals 1, and that is 2 over 2 actually, right? That'll be the first 2 terms in each sequence. Well, for n equals to 2, in this case, we keep the first term that we already got, and then we do the 3 times, or the 2 times 2, which is 4, and 3 times 2, which is 6 minus 1, that's 5. For n equals to 3, keep the ones that we already have, that is 2 and 4, 2 and 5, but we multiply by the next ones. In this case, for n equals to 3, that's 2 times 3, which is 6, and 3 times 3, which is 9 minus 1, that's 8. So we keep just adding the new factors by keeping the ones that we already did. All right, how does the ratio test is going to work for a problem like this. All right. So, as usual, set up a limit. Limit a sub n plus 1 over a sub n as n approaches infinity. All right. So, okay, before setting up the limit especially for the a sub n plus 1, because usually that's what I think the one students have a lot of issues with the n plus 1 term. So, for example, okay, what if I want to list the product of the first 50 numbers, all right? And well, I'm not going to write 1 times 2 times 3 times 50. I'm not going to write 50 numbers. There's actually compact ways to write those products. So if you want to write this on the back side of your page, that'll be perfect, because that's not part of what we're going to do here. So first 50 numbers. So this is, for example, 1 times 2 times 3 times 4 times, well, I'm not going to write all of them. I'm going to write dot, dot, dot. And that's to indicate that the product continues. And then I can write the last 2 or the last 3 or the last 4, depending, you know, like times 49 times 50. Alright, that's how we write the product of the first 50 numbers in compact form. Another way to write this 1 times 2 times 3 times 4, maybe I need one more number to show up, the 48. Alright, maybe I need the 47 to show up, 1 times 2 times 3 times 4 times 47 times 48 times 49 times 50. So where are we going with this? Well, so we're going to need this when it comes to shifting the last term, in this case in the general sequence, to n plus 1. Alright? In the same way that we wrote the factorials of the numbers in different ways. For example, 5 factorial is the same as 5 times 4 times 3 factorial, for example. Another way to express the 5 factorial is 5 times 4 factorial. Maybe 5 times 4 times 3 times 2 factorial, depending on what do we need to cancel. Well, so number 1, this is limit absolute value of -1 to the n plus 1. So this is 2, 4, 6, dot, dot, dot. I'm going to leave a space here for a purpose. You'll see why. 2 times n plus 1. All right? Divided by 2 times 5 times 8 times dot, dot, dot. 3 times n plus 1 minus 1. Oh, and again, I'm going to leave some space here. I'm going to leave a space for something. So, this is going to be divided by the original, -1 to the n, 2, 4, 6, dot, 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 2 to the n. We're not doing any shifting on the original, just the original. 2, 5, 8, dot, 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 3n minus 1. So that's limit n approaches infinity. Okay, let me make more room for this. Well, actually, that's fine. Alright, number 1, we can get rid of the alternating factors because it's an absolute value expression, right? And well, I'm still going to leave this space right here. So to add something that I will add in a second. So let me put a question mark, question mark, question mark. All right. So I'm going to divide, or rather, I'm going to multiply by the reciprocal of the denominator, and at the same time, I'm going to simplify this one right here. All right, so limit n approaches infinity, absolute value of 2 times 4 times 6 times dot 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 space, that's 2n times 2, or plus 2 rather, that's 2n plus 2, divided by 2 times 5 times 8 dot dot dot, leave a space, that's okay, that's going to be a 3n plus 3, but minus 1, that 3 minus 1, isn't that a 2? So that's going to leave us with 3n plus 2. Alright? So, then I'm going to multiply by the reciprocal of this one, 3n, or rather, 2 times 5 times 8, dot dot dot, 3n minus 1, over 2 times 4 times 6, dot dot dot, 2n. Alright? Well, our goal in the ratio test, just like the previous example, let me go back real quick. So did you see how we expanded factorials to cancel factorial terms? Do you see how we also use laws of exponents to cancel these exponential terms? Well, so we want to cancel these chunks of factors. However, here is the thing. Here I cannot factor 2, 4, 6, 2n plus 2 with 2, 4, 6, 2n, because these are not these are not equivalent chunks of factors, all right? So we cannot do this, and we cannot cancel. So you might argue, well, we can cancel 2, 4, 6 with 2, 4, 6. No, if we're going to cancel, we have to cancel the whole thing. So this space right here I left in blank is to write the second to the last term. So what's the second to the last when we shift by n plus 1? Isn't it the same as 2n? See, did you guys following me here? Well, what's the second to the last for 3n plus 2? It's the same, 3n minus 1. Alright? In the same way that we have like 1, 2, 3, dot, 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 50. Alright? Well, in this case, I need 1, 2, 3, dot, dot, dot. I need the 49 to show, which is the previous factor. Yes? Well, because in this case, we shifted the n by n plus 1. This n plus 1 makes it a 3n. And 3n plus 3n, I mean 3 times 1, which is 3. 3 minus 1, oh, that's a 2. Thank you. Yeah, that one should be a 2. Use the correct color. And well, only then we should be able to divide this out. 2, 4, 6, 2n with 2, 4, 6, 2n. 2, 5, 8, 3n minus 1. 2, 5, 8, 3n minus 1. What is going to be left in our limit? Ultimately, limit n approaches infinity, 2n plus 2 over 3n plus 2. And the limit in this case, because polynomial over polynomial degrees match, this is 2/3, which is less than 1, and converges by ratio test.